from the normal distribution and standard normal distribution, we'd like to define other random variables. Yeah, chi-squared. How to define the chi-squared random variable? Yeah, we have the z. Okay, suppose that we have a k z. Okay, that are the random variables. If they follow n 0, 1, okay, which means standard normal distribution. Okay, so we suppose that on the z follow the standard normal distribution. Okay, okay, then they are also independent. Okay, okay, and now I'd like to take that chord. Okay, and we sum them up. Okay, so in this case, we take we are interested in z1 squared plus z2 squared plus up to zk squared. Okay, and this way we get the new random variable that following the chi-square distribution with degree freedom k. Okay, so don't forget the k. K is the degree freedom, one parameter of the chi-square distribution. Okay, k will determine the form of the chi-square distribution. Okay. Okay, so you can see right away that chi-square random variable is always positive. In the special case, we get 0, 1. Okay, and you can also prove that this expectation is k and variance is 2k. Okay, some examples for the chi-square distribution with df. Okay, when df equal to 10, degree of freedom equal to 10. Okay, get this first curve. 30, you get the next curve. Okay, and 15, you get the third curve. Okay, so what can you observe? You have the feeling that the distribution becomes more and more symmetric as df increases. Okay, as df increases from 10 to 30 to 50, the distribution seems to be more and more symmetric. Okay, so let's take a look at the properties of the chi-square distribution again. Chi-square random variable cannot be negative, so it's bounded by 0 on the left, skewed to the right. This chi-square distribution is not symmetric and skewed to the right. Right tail is longer. Chi-square distribution will approach a normal distribution. You see that chi-square distribution will approach normal, which is symmetric, as df increases. Okay? As df increases, exactly this way. Okay, and also the sum of independent chi-square random variable is also a chi-square random variable. Okay, suppose you have a several chi-square random variable. As long as they are independent, you take the sum, and finally we also get the chi-square random variable. Okay. Next, how to define a t random variable. Okay, and how to get a t random variable. Okay, we also call it the student distribution. Okay, suppose they have z1 following a standard normal distribution, okay, which is n01. Okay, chi-squared random variable, I didn't know this one, huh? Is the random variable following chi-square distribution with degree freedom k. Okay. Okay, so I take this random variable divided by k. And we also suppose that that1 and chi-squared random variable are independent. Okay, independent. Then you take the ratio of that1 to square root random variable divided by k is degree of freedom. Okay, the result will follow a t distribution with degree of freedom k. So again, k is the parameter determining the form of the distribution. Okay, let's take a look at the t distribution when degree of freedom is equal to 20. Okay. Yeah, so okay. Oh, you see this curve. Okay, you see that this curve here is flatter because the peak value here is smaller than the peak value of the standard normal. Okay, and has flatter tail. You follow the curve, you see that okay, the tail is somewhere here. Flatter tail than the standard normal distribution. Okay. Now, t distribution, first of all, is symmetric distribution. Symmetric over 0. With effective value 0, variance df divided by df minus 2. Okay, it has flatter tails than the standard normal, and it is flatter than the standard normal distribution. Okay, so again, okay, if you take the first df equal to 10, you increase the value of df 20, 30, and so on. You see that we approach the standard normal distribution. Okay, let's define this point. Yeah, so before I can see the standard normal in 0, 1, like the limit case of the t distribution. Okay, so it can be seen as t distribution with degree of freedom infinity. Okay. Okay, finally, okay, very often with statistics and econometrics, we often have to work with the ratio. Okay, ratio in many cases the ratio will follow the f distribution. Okay, besides the t distribution as we defined before. Okay, here you also have the ratio. Okay, of z divided by chi squared. Yeah, the ratio of the two chi-squared random variables. Okay, we start with the chi-squared distribution. Yeah, so chi1. Okay, here squared is the first chi-squared random variable. Okay, we denote it by chi1. So I have to say that it's a random variable following. Okay, chi-squared distribution. Okay. Okay, with degree of freedom k1. So actually we call it chi1, but actually it's random variable following chi-square distribution with degree of freedom k1. So k1 is the degree of freedom. Yeah, so for the notation, chi2 squared, okay, follow chi-square distribution with k2 as degree of freedom. Okay. Okay, and they are independent. You see that. Okay, very often we propose that the individual random variables are independent. Okay, and what happens if we take chi1 right here divided by its degree of freedom over okay, chi2 squared divided by k2. Okay, okay, so the result will actually follow what called the f distribution with two degree of freedom. Okay, k1 and k2. Okay, now f distribution is determined with two degrees of freedom, k1, k2. Okay, okay, k1 is called the numerator degree of freedom, which is the degree of freedom of the first chi-squared random variable. Okay? K2 is the denominator degree of freedom, which is the degree of freedom of the second chi-squared random variable. Okay, so this ratio will follow the f distribution with two degrees of freedom k1 and k2. Okay, let's take a look at the example of the F distributions. Okay, here when K1, K2 are 25, 30, and the next one K1, K2 are 10, 15. Okay, so you see that actually the curves, okay, move along, right? Okay, so first of all, F random variable cannot be negative, so it is bounded by 0 on the left. F distribution is skewed to the right, okay, like the chi-square distribution, okay, and it's determined by the numerator degree of freedom K1 and denominator degree of freedom K2. Okay. Okay, no questions to now. Okay, so there have been the main probability distributions you have to work with in this class econometrics. Okay, and you use them to determine the confidence interval and especially to test hypothesis. Okay. Okay, so let's move on. Okay, and remind you what are the estimators. What are the estimators? By definition, okay, an estimator is the sample statistic that we use to estimate the parameter. Okay, so you remember that first of all, statistics can be divided into two sub areas: descriptive statistics and what inferential statistics. By inferential statistics, we'd like to say something about the parameters from the samples. Okay. So again, the population is the set of all objects or people of your interest. Okay, so very often the population is very big, like the population of all students in Vietnam. Okay, population of all students in Vietnam. Is this example again later? Okay, for example, the population of all students in Vietnam, and then the features of the population are called parameters. Okay, so we have the parameters defined as the features of the population. And so in this way, actually the parameters are unique, but often unknown. Okay. Okay. Unique, but unknown. For example, if I am interested in the average age of all students in Vietnam, in this case, okay, we call it mu, average age. Yeah, and I know that this value exists, but yeah, it's very hard to know what is the true value of mu. And so mu is unique, but unknown. Okay, oh, I would like to work with something okay, smart in the sense that now, okay, because it's impossible to work with the population, I take a sample. Example of sample of 200 students. Okay, so and then I determine the corresponding feature of the sample, so average age, for example. Okay, so it's possible to collect the sample. Okay, to ask people in my sample, what are you? And I get all the values, and then I get the average age of all students in my sample. Okay, okay. So X bar is what I call statistics. Yeah, statistics, and the formulas to calculate the statistics. It can be seen as the estimator. Okay, so estimator is simply a sample statistics. In this case, it's a statistic. And the estimator is simply a sample statistic, okay? And it's given by a formula that we use to estimate the parameter, okay? Because mu is unknown. Okay, then I try to get x bar from my sample, and I like to say something about mu from x bar. Okay? So it's an example of what we call the inferential statistics, saying something about the parameters using a sample statistics. Okay, right? Okay, so you're okay. Remember, right? The most commonly used estimators. Okay, when I talk about the mean, like the average age, mean or average. Huh? Okay, the mean. Okay, so in this case, so if we are interested in the mean as the parameter, then the corresponding statistics is x bar. And here it is a bar. This bar, you know, on the average, you all know, you take the sum of the values divided by n. Okay, that's 1 plus this n divided by n. Right? Okay, how about the variance? Okay, very often we denote the variance by sigma squared. Okay, so the corresponding estimator is the sample variance. Okay, for the sample variance, remember the way to calculate the sample variance? Squared equal to, okay, the sum on the x I minus x bar squared divided by what? Divided by what? Because here you have several options, right? But a good way, okay, to calculate the sample variance is to divide by n minus 1. Okay, you remember why? Because here we adjust by degree freedom. Okay, and from our sample of size n, then we have a degree freedom equal to n. Okay, but by using x bar, which is the average. Okay, by using x bar, we mean that we lose 1 for the degree freedom. Okay, that's why it's better to divide by n minus 1. Okay, better in the sense that you get a better property for the sample variance. Okay, calculated this way. Okay, and this estimator will become unbiased. Okay, if you don't know about this, okay, and you just take this sum divided by n. Okay, so you just take this sum divided by n, then you still get an estimator which is consistent but not unbiased. Okay. Okay, so the good way to calculate the sample variance is this one. Okay, take the sum of the difference squared divided by n minus 1. Okay. Okay, you can easily check the sample variance formula in the textbook. Okay, in standard deviation, of course, sigma. Okay, is statistic or estimator, and simply the standard deviation calculated from the sample variance, okay, that we denote by S. Okay, proportion we don't use in this class, okay, but in statistics, you probably remember it is B hat, sample proportion. Okay. Okay, and okay, some estimators are good, some others are not so good. Okay, of course, we'd like to work with the good estimators. Okay, the estimators are good when they are unbiased, efficient, consistent. Right? Okay, let's see what it means. And then let's take a look at this slide. Compare unbiased and biased estimator. Okay, which one is better? Which one is better? What do you think? Okay, clearly, okay, without knowing anything, right, you will have the feeling that the first one is better. Okay, first one is better. Again, this one is better. Okay, you say that the estimator is unbiased. Okay, why? because actually we target. Okay, you are on target here. You are on target. Okay, so you can try the first time, right? You can try the first time, get the first value here. You can try the second time, get the value there. Okay, but the feeling that on average, if you take the average of all these values, okay, you are on target. It means that the average of them all will be equal to the true value. Okay, I'll translate it by the fact that we write down expectation of the estimator within the theta hat is equal to the true value of the parameter theta. Okay, so theta hat is the estimator, okay, or statistic. Okay, we calculate using a formula from the sample, okay, equal to the true value of the parameter. In this case, we say that the estimator is unbiased. Okay, compared to the next case, when the estimator is biased. Okay, it doesn't look very good, right? Okay, because it's off target on average. Okay, you get this and you take the average, you get something here. Okay, which is not the true value. Okay, so in this case, expectation of the estimator is different from the true value of theta. Okay, and this difference is called the bias. Okay. Okay. Okay, the estimator is efficient when it's also a good property of the estimator efficiency. Okay, the estimator is efficient if it has the small variance. Okay, then automatically more standard deviation. In the best case, you have the minimum variance. Okay, so let's compare the first and the second diagram. Okay, which one looks better? Okay, clearly you see that again, you prefer, right? First one. Because the first try, okay, yeah, okay. Because you see that the first try, okay, maybe here, the next one there, okay, they look quite close, right? To the target. Compare to the second case. Second case, here you are quite far away. And the next one also closer, but yes, they are all quite far away from the target. Yeah, and then efficient estimator is the one giving you, okay, the value closer to the true value of the parameter. Okay. Yes, so it's measured by the variance. Okay, so when the estimator is not efficient, we say that it is inefficient. Okay. Okay, sometimes the estimator is not unbiased. It means that, okay, sometimes the estimator is biased. Okay. For example, when you calculate the variance, okay, sum of the squared difference divided by n. So in this case, it's biased. But the estimator is still good in the sense that it is consistent. Okay, so consistency is weaker than unbiasedness. Okay, okay, weaker than unbiasedness, but consistency is important. Okay, the estimator is said to be consistent if the probability of being close to the parameter estimate increases, the sample size increases. Okay, intuitively, you take the first sample with size 10, second sample with size 100. Which one is better? Which one is better? It makes sense that there. Okay, what do you say? I love the message. The second one, right? Okay, intuitively, when you have a big good size for the sample, you should get better results. Okay, it makes sense Yeah, but it also means that actually when the sample size increases, like in this case greater than 10, probability of being close to the parameter is estimated increases. Okay, it means that we get a better result as the sample size increases. Makes sense. Okay, so in this case, the estimator is consistent. Okay, and again, it is a good property. Okay, okay. So for the estimator we want to work with, at least it must be consistent. Okay, so they have been the good properties of the estimators that we use all the time. Okay, so now in inferential statistics, okay, the two main sub areas, I could say, two main sub areas of inferential statistics are what I call confidence interval and hypothesis testing. Okay, now let's work with the confidence interval or the interval estimate. Okay, basically there are two types of estimators: point estimate and interval estimate. Okay, by definition, a point estimate give you a single value estimate. Okay, for example, when I'm interested in the mu parameter, which is the average age of all students. Okay, it's been known, right? Okay, okay. For some reason, okay, if I take a sample, you can create the average age of students in my sample. Okay, I get one value of F bar. Yeah, so I take a sample of 100 students. They collect the age. I calculate X bar. For example, I get the value 19.8. It is the point estimate. It means a single value. Right? Okay. It is good, but actually you don't know whether this value is far away or close to the true value of the parameter. Right? Okay. So the point estimate conveys little information about the actual value of the population parameter, in this case is mu, or the accuracy of the estimate. Okay, so that's why we prefer to work with the interval estimate or the confidence interval. For the point estimate, you get a single value. Confidence interval, or I get an interval. And giving you the range of values that we believe to include the true value of mu. For example, I get an interval like this. Okay, I say that here it is my interval estimate. Okay, and I am 95% confident that my interval contains the true value of mu. Okay. Okay, so associated with this interval, we have the level of confidence. Okay, we go 95%, sometimes 90%, sometimes 99%. Yep. Okay. Again, for the interval estimate that we call confidence interval. First of all, you give the interval, and the interval is associated with the level of confidence. Okay, that the interval contains the true value of the parameter. Okay, and let's work out one example to get the confidence interval here. Okay, we need to use now the central limit theorem. Okay, down. Okay, so well, let's try to get the confidence interval. Okay, starting with the central limit theorem, saying that if I have n, when the variables x1, x2, xn, they all follow the same distribution. Okay, with the mean mu, variance sigma squared. Okay, and they are independent. Okay, and it's large enough, like greater than 30. And then, okay, what we get? The sum. Okay, will approximately follow the normal distribution with mean and mu, variance, and sigma squared. Okay, and then because I like to work with the X bar, okay, the average, okay, like the average is, yeah, define as the sum divided by n will approximately follow the normal distribution with mean, what is the mean? Okay, and mu divided by n. Okay, and how about the variance? This is the variance. And sigma squared divided by what? Okay, okay. Okay, divided by n or n squared. N or n squared. Yeah, n squared. Okay, why? Remember? Because, okay, n squared, right? Okay, because when you take this divided by n, right, for the variance, with the factor, it becomes n squared. Okay? Write it somewhere here. So for example, bar, yeah, z divided by 2, okay, is equal to what? Bar z. If I want to move 2 outside, I get 2 squared. Okay? I get 2 squared. Okay? 2 outside, I get 2 squared. I can get right there. Okay? 2 squared, I get 1 over 4. Okay? I get 1 over 4. Right? Okay? So the x bar will approximately follow this normal equation. And then I can simplify. Okay, here. Okay, and divide by n, I get mu, the mean. And there, okay, n and sigma squared. I get sigma squared divided by n. Okay? So one step further, then x bar minus mu divided by standard deviation, which is sigma over root n, will follow the normal distribution, right? With mean 0, variance 1. Okay? Okay? And now, follow the confidence interval. Okay? Confidence interval. Okay? But confidence interval is given with the level of confidence, right? I just wonder what is the confidence interval. Okay, at for example here, like 95%, 95% confidence level. Okay, I like to get the confidence interval 95% confidence level. Okay, so how to get this? And okay, I use the fact that the statistic follows the normal distribution. and then I draw the N01 standard normal distribution. Okay, and clearly it's symmetric with the value 0 here. Okay, I wonder what is the interval containing 95% of the population. Okay, 95% of the population is 0.95. Okay, so I wonder what is the symmetric interval containing 95% of the whole population. Okay, so clearly symmetric about the value 0. So okay, I want to capture actually 95%, okay, of the whole population. Okay, clearly I can move over the here within this interval. Is that right? Okay, so I wonder what is this value, what is that value? Remember what they are. Okay, you can refer to any statistical table for the standard normal distribution. Right? Okay, so if you have 95%, okay, the population here, so what is left is 5% for the 2 tails. Okay, divided by 2, I get, okay, 5%, 0.05, 0.025. Okay, and what is this value? What is that value? Okay, which is what we call the z-score. Z0.025. Okay, and by symmetry, this one is simply the negative value. Negative z 0.025. Okay, remember what value is it? Okay, you can check, right? You can check. Okay. 1.96. Okay, so we get 1.96. Okay, and there negative 1.96 from the table. Okay, any statistical table will give this values. Okay, so what does it mean? It means that I can say that okay, now I already got the interval capturing 95% of the population. Okay, then I can say that the probability that my statistic x bar minus mu divided by sigma output anything here x bar minus mu okay, divided by sigma over n, okay, to belong to this interval is 95% of 1.5. All right. Okay. Okay, clearly 1.96. Yeah, negative 1.96. Okay. Okay, probability of this statistic, yeah, to belong to the interval minus plus 1.96 is equal to 0.95. Okay, and one more step. Okay, I'd like to see another way to transform it. Okay, I just want to write down differently. So it means x bar minus mu less than 1.96. Okay, sigma over n. Okay, over here on the left, I get negative 1.96 sigma over n. All right. Okay. Okay. And then I move mu, okay, to the left hand side and right hand side. Okay, mu plus 1.96. I mean, not mu. No, it's what I want to get is mu. Okay, not okay from S so it is mu. Okay, what I want is mu. Okay, so if we move to the side. Okay. Okay, so I want to get the interval for mu. Okay, mu S bar minus. Okay, 1.96 sigma over. Okay. Okay. Then what can I say next? Okay, remember that again, mu is the parameter. Okay. Unknown parameter we'd like to estimate. Okay, F bar is the statistic, okay, that I can calculate for my sample. Here, that one is known. Okay, here also known. Okay, so then I get the interval. Okay, X bar minus. Okay, and X bar plus 1.86 sigma over 10. Okay. Okay, and I can say that I am 95% confident that my interval, and now my interval is known. Okay, from the value of F bar known, okay, I can say that I am 95% confident in that this interval I here contains the true value, okay, of the parameter, okay, or value of the mu. Okay. Okay, here we cannot say about the probability anymore because mu again is parameter, is the number which is a constant. Okay, we don't know it, but actually it's a constant. It's not like X bar. X bar varies according to the sample, but mu again is unique. Okay, so we cannot say that actually the probability for mu to belong to something. No. Okay, we say that we are 95% confident that this interval contains the true value of mu, okay, of the parameter mu. Okay. Okay, so it's a way to get the confidence interval. So again, we start from the central limit theorem. Okay, we use it, we get the standard normal distribution. Okay, right now for X bar minus mu, okay, we transform, we draw the interval capturing 95% of the population. Yeah, and then I get an interval. Okay, I transform it. And finally, I get the interval I, okay, containing the value of mu parameter at 95% confidence level. Is that okay? Okay. So I'll save this. Okay, so we got it, right? We got it. I can get it back. Okay. I can get back here. Okay, we can get back to the slide. Okay. Okay, we're gonna again check the details. Okay. The details on the slide. Okay, this way you get the confidence interval. Okay, at 95% confidence level. Okay. Okay, confidence interval. Okay, first of all, gives you some idea about the true value of mu associated with the level of confidence. Okay. Confidence interval can also help you test hypothesis. Okay. Not all the time, but sometimes, especially when you have two-tail test. Okay. When you have two-tail test, confidence interval can help you test hypothesis. Okay. So let's move on to the next section on statistical hypothesis testing, which is very, very important in econometrics. Okay, we test hypothesis all the time. Okay. Okay, it's easy to understand because associated with any model, we have a parameters. Okay, for example, if you talk about the normal distribution, okay, the parameters are mu and sigma. Okay, so we'd like to say something about the value of mu, about sigma, or associated with a linear model, we have some coefficients that are also the parameters. Okay, so okay, taking a sample, collecting data, get some statistics. I'd like to be able to say something about the coefficients, for example, positive or negative, okay, greater than 1, smaller than 1, okay, regarding the coefficients. Okay. Just good. Maybe for regression we will discuss later. Okay, so basically, what is hypothesis testing? Okay, again, hypothesis testing is one part of inferential statistics. I'd like to say something about the parameter from the sample statistics. Okay. Yeah. So for hypothesis testing, first of all, we test with the significance level. Okay. So significance level that we call alpha, okay, by often, right? Which is the level of significance. Often we want alpha to be small. Level of significance. Right? Okay, hypothesis testing. We start with the non-hypothesis. Non-hypothesis, which is a statement about the population parameter. Okay, so when I consider my population with all students in Vietnam, yeah, I give a statement. Okay, I say that in my opinion, the value of mean average age of all students in Vietnam is equal to 21.5. Okay, as an example of the non-hypothesis, okay, a statement about the population parameter mu. Okay, it is my opinion. So, okay, why not? Yeah, can give it. And say that, okay, in my opinion, average age of all students is equal to 21.5. Okay. Okay, and of course, it's my opinion, and you may disagree with me. Okay, you don't agree with me. Okay, if you don't agree with me, you want to find a way to prove that I'm wrong. Okay. Okay, so you want to find a way to prove that I'm wrong. And by doing this, we actually test hypothesis. Okay. So H1 non-hypothesis. Example this one. Okay. H1 alternative hypothesis denoted by H1 is simply not HO. Okay, the negation of HO. Okay, so in this case, mu different from 21.5. The negation of HO. Okay. Okay, so on the null hypothesis, we can get the alternative hypothesis. Okay, and remember that HO is what is often a belief. Okay, it's my opinion. Okay, when I say something, it is what I believe in, right? Yeah. Okay, it's often a belief. Okay, and anything else about HO? HO is a belief. And HO is a statement that we give from the beginning, right? Okay, so later on, okay, if you don't agree with me, right, you take a sample, okay, do something, okay, and in the end, okay, you make a decision. You make decision to what? To reject HO or not reject HO. Okay. Okay, so again, right, now hypothesis HO is a statement about the population parameter. Often it is the belief. Okay. Okay, in alternative hypothesis, H1 is the negation of HO. Okay. And you disagree with me. So in this case, actually, your collector you find evidence. Okay, for example, like here, you calculate the test statistic, and finally, you come up with a decision. To reject HO or not. Is that okay? To reject HO or not. Well, remember, we start with HO. Yeah. Now hypothesis, okay, from which you can write out H1. Okay, you collect evidence. Okay, do something right here, and finally you make decision. Okay, two decisions only: reject HO or not reject HO. Okay, what is the difference between the two? Okay. After collecting data, okay, if you get enough evidence to reject HO, in this case, you say that you reject HO and you prove H1. Okay. Otherwise, you cannot reject HO, and somehow you have to accept it. Right? Accept HO. Okay. Accepting HO because you cannot reject. Okay. It doesn't mean that you prove HO. Okay. Okay. The difference between the two. Okay. In hypothesis testing, okay, in the best case, you can prove H1. Okay. But we never prove HO. We only accept HO. There's a belief you accept HO because you cannot reject it. When you can reject HO, then you already proved H1. Okay. Yes. So okay, HO and H1 play different roles in hypothesis testing. Okay. So in social science, it's important. Okay, when you say that, okay, now for example, okay, there has been a crime and a person was arrested. Okay, so in this case, HO, okay, has the belief to say that the person is innocent. Okay, it means that you have to believe that the person is innocent until when you have enough evidence to reject it. Yeah. Okay, to reject it, in this case, you can prove that the person is actually guilty. Okay, and the person has to go to jail. Okay. Okay, but if you don't have enough evidence to reject HO, then you have to accept the fact that the person is innocent. Okay, and the person is free. Right? Okay, so in social science, it is exactly the case. You have to believe that the person is innocent until when you have enough evidence to reject. Okay? Okay. So again, the only statement you may be able to prove is H1. Yeah. Okay, when you cannot prove H1 means you cannot reject HO. In this case, actually we somehow accept HO. Okay. Okay, it's very interesting. Huh? Okay, with the hypothesis testing. Okay, it's very different from the normal, the usual mathematical proof. Yeah? The mathematics have to prove everything. Okay, but here, actually remember that in the best case, you can prove H1. Okay, when we cannot prove H1, we accept HO. Okay. Okay, so of course, for HO and H1, actually HO can be true or false. Okay, when I say that, okay, in my opinion, the average age is 21.5, okay, can be true or false. Okay, and when you disagree with me, you take a sample, you collect data, you make a decision to reject HO or not reject HO. Okay, according to different cases, we obtain this contingency table. Okay, with 4 possible cases. Okay, for HO can be true or false. Okay, and when you make a decision, you may be able to reject HO. Okay, so in this case, okay, for example, if HO is true and you reject it, then you get the error. They're called the type 1 error. If HO is false and you reject, it is the correct decision. Okay? Okay, and when you decide not to reject HO, okay, and if HO is true here, then it is the correct decision. Okay, otherwise you fall into this case of the type 2 error. Okay? Okay, so we call alpha probability to get the type 1 error, and beta probability to get the type 2 error. Okay, and actually in practice, we focus our attention on controlling the type 1 error probability via alpha, which is the level of significance. Okay, we want alpha to be small. Okay, for example, 5%. So in this case, we test hypothesis 5% significance level. Yeah? So we like to control probability for this because we don't want this to happen often. Yeah? So often we choose alpha like 5%, most common case, or 1% or 10%. Okay, if we want to unlock a little bit. Okay. Okay, so again, okay, in practice, we like to be able to control the probability to get the type 1 error. We want it to be small via the level of significance, for example, 5%. Okay? Because this case is more important to avoid. We don't want to reject HO when HO is true. Okay? So it means that when the person is innocent, we don't want to put the person in jail. Okay? Or in this case, we like to control this value alpha. Okay, and for the test, let's make the difference between the two-tailed test and one-tailed test. Two-tailed test, third case. Okay, two-tailed test, when we test the parameter is equal to something, and then the alternative hypothesis to say that parameter is different from this value. Okay, so why we call it the two-tailed test? Yeah, so of course we collect data from a sample. Yeah, we calculate the test statistic. Yeah, and hopefully it follows the distribution that we know, for example, normal distribution. Okay, and we draw the normal distribution. Okay, so from any normal distribution, we can transform to get the standard normal distribution. Okay, then we draw standard normal distribution. Yeah. Okay, and clearly, okay, after getting N01, it means that we want the test statistic to be supported by HO. Okay, supported by HO, okay, or not actually, you see, according to what called the rejection function. Okay, so after drawing N01, you see that you have two tiles on the left and the right. Okay, example will also give you the value x bar. Okay, intuitively, if x bar is close to 50, then okay, HO is supported. Okay, if x bar is far away from 50, okay, clearly you have the feeling that we like to reject HO. Okay. Okay, so when x bar is close to 50, we calculate the score, okay, corresponding to the test statistic. Actually, we want the test statistic to be close to 0 if sometimes. Okay, so we don't want to be far away from the mean. Now, on this case, when this far away from the mean, is say that actually we have the rejection region. Okay, on the right, when X bar is far away from 50, and also here when X bar is far away from 50, okay, but now on the left, okay. So the two-tail test is a test even associated with the form of the rejection region. You see that in this case you have two-tail. Okay, for the rejection region, call it the two-tail test. Okay, so the name comes from the rejection region location. Okay, when I have the rejection region on the right, on the left, it means all the two tails we call the two-tail test. Okay. Okay, similarly, so it means that you have to look at the H1. Okay, similarly here, when you want, okay, only one side of mu, H0, when they say the mu is smaller than 50, and then H1 mu greater than 50. Okay, you reject H0 when mu is far above 50. Okay, you get something here far above. Now the rejection region be on the right. Okay, that's why you call it the right tail test. Okay, for the second case, we reject HO when test statistics X bar is far below 50. And then you can draw something like this, far below, on the left tail. Yeah, so we call it the left tail test. Okay, these two cases are called the one-tail test, different from the two-tail test. Okay. Yeah, so the name of one-tail test or two-tail test comes from the rejection region. Okay, form. Okay, either you have two tails, you have only right tail or left tail. Okay, you can see better here. Okay, two-tail test. The test in rejection region when after accumulating X bar, okay, X bar far away from this value we want to test. Yeah. Okay. So for example, okay, we want to test if mu is equal to 1000, but X bar you get 2000, 10,000. It's too far away, so clearly we would like to reject H1. Okay, so it means that when X bar is too far above, like here, or too far below, we reject H1. Yes, in this case, we call it a two-tail test. Okay, in this case, okay, you want to test this. Okay, of course, you reject it if X bar you calculate is very small compared to 1000. Okay, for example, 0.1. Okay, for example, okay, so it seems to be too far below. Okay, the value of 1000, in this interval. So in this case, we like to reject when the bar is far below, which means on the left. We call the left hand test. Okay, similarly for the right test over here. Okay, when you want to test this mu with smaller than something in it. Okay, you reject when X bar is far above 1000. Okay. Okay, so again, by definition, the rejection region of the statistical hypothesis test, the range of numbers that will lead to reject H1. Okay, so the idea of the rejection region is actually a region just like before. When so after determining within the rejection region here and there, right? Okay, if my TS belongs to this, then I reject HO. Okay, it is the case for the two-tailed test. Okay, if my TS belongs to this, also I reject. If my TS belongs to this interval, I do not reject H1. Okay? Okay, and the values are called critical values. Okay, sometimes I have only one critical value. Here in this case, I have two critical values. Okay, critical value. Okay, the value which will help you determine the rejection division. Okay, we often obtain it from a table, statistical table. For example, when I want to test at 5% significance level, so 5% is the area of the rejection region. So I divide 5% by 2, I get 2.5% here, 2.5% there. Okay, following the standard normal distribution and 0, 1, then I can get this value Z, okay, from the table. Okay, so this is simply Z 0.025. Is that okay? Okay, 1.86. Okay. So again, critical values, critical points are determined from the table. Okay, after fixing the value alpha significance level. Okay, critical points from the table. Rejection region, okay, you determine the form of the tail or one tail, etc. from what? Okay, determine the form from HO and H1. Okay. Okay. So again, rejection region will help you decide, okay, if you reject it or not. Okay, if test statistic belongs to the rejection region, we reject H1. Okay. Okay, and now again, for testing hypothesis, actually you have three approaches. Okay, three approaches. Okay, let's discuss the one using the confidence interval before. Okay, and it only works for the two-tailed test. The confidence interval can help you test that hypothesis only for the case of the two-tailed test. Okay. Okay, and how? Maybe let's point out something here. Okay, I like to test to test only. So I like to test now as own. Like in my example. Okay, I want to test. Maybe it's not a good right now. I change. Okay. Okay, now I like to use the confidence interval to test hypothesis. Okay. Okay, that's the second way to test hypothesis, okay, on my slide. Okay, for example, I say that, okay, in my opinion, average age of our students is 21.5. Okay. Okay, and clearly, from HO, I can get H1 right away. Different from 21.5. Again, then you can tell me right away if the two-tailed test or not. Yes or no? Okay, you can see right away the two-tailed test. The test, yes. Okay, now, okay, step by step, I say that mu is 25.1.5. You don't agree with me. You don't agree with me. So we want to prove, yeah, that I'm wrong. Okay, by taking a sample. So we take a sample of n students. Okay, for example, n is equal to 100, right? Yeah, and then you collect data. You ask hold you to all of them. You get the average. Average, for example, I don't know. Yeah, average age, for example, you get 23.2. What do you think? Okay, already, okay, after getting the value of x bar, you can already compare. But of course, when you compare here, just intuitively, 3.2 compared to 21, 10.5, we don't know. Okay, it's a bit different, but is it big enough, okay, to reject HO, my HO or not? I don't know. Okay, so the idea, of course, and here again in hypothesis testing is to see that if x bar is close to the value of mu that I like to test, okay, this value is often what I call mu zero. Okay, sometimes mu star. Yeah. Okay. On the slide or in the book, sometimes you see mu zero or mu star. Zero means no hypothesis. Okay, so the idea is to see that, okay, if x bar is close to mu zero, then we do not reject. Okay, it means that actually the value is close, so somehow HO is supported by the data. Okay? So the value of mu zero is supported by data. Okay, or zero in this case. Okay, and if x bar too far away from mu zero, okay, in this case you can reject HO. Okay, so if you know the confidence interval, for example, if I want to test, okay, now I fix the value of alpha, okay, from 5%, okay, significance level 5%. Okay, so in this case, confidence interval, okay, after looking at this, you know that it's a two-tailed test. Okay, so I can use the confidence interval. Right. Confidence interval was to have the test hypothesis, okay, and I want to test at 5%. Then now I like to look for the confidence interval at how many percent? Okay, in this case, if I want to test at 5%, I have to look at the confidence interval at 95%. Okay, confidence level. Yeah. So let's see if I get it from the slide before. Okay, my confidence interval. Okay, let's see if it works. My confidence interval is what is it? X bar plus minus 1.96, right? Sigma over root n. Okay, so depending on the value of sigma as well. So suppose that sigma is equal to, okay, let's take sigma is equal to, for example, equal to 2. Huh? So just this. Okay, confidence interval. I replace. Yeah. I got what? I get 23.2 plus minus 1.96. 2 divided by root n, root 100 equal to 10. Okay, and what do you get? Yeah, 0 point here, it is 0.2 times 2 approximately. Okay, it's 2 times 0.4 approximately. Okay, I'll try to go fast. Then okay, what do you get? Yeah, so my interval is the interval minus 0.4, 22.8. Okay, and I take the plus I get 23.6. Is that right? Okay. Okay. Oh, this one is mine. Okay, it's okay, right? Okay, so I try to go fast. And here, what interesting is the way to use this confidence interval, right? Okay, you see that my confidence interval is 22.8 to 2.6. Does it include my value mu zero or not? What is mu zero? Okay, mu zero, in my opinion, I said that, okay, HO, in my opinion, okay, the true value of mu is 21.5, right? Which is the value mu zero. Okay, and you see right away that the confidence interval, okay, doesn't include the value mu zero. Okay, so here it is my confidence interval, but my value mu zero is here, okay, outside. So what do you think about the decision? Would you reject or not reject? Okay, decision. We do not reject. Yeah, right. Okay. So you reject if this interval doesn't include mu zero. Okay, you do not reject if this interval includes mu zero. Okay, so again, if I only two cases, right? Okay, so in this case, it doesn't include mu zero, then you can say that actually HRO is not supported by the data, okay, or the sample, right? So in this case, I reject HO. Okay, so in this case, you already proved H1. Okay, okay, now you're happy to say that, okay, you already collect data, right? You found enough evidence to reject my statement, okay, and to say that I'm wrong. Is that okay? So it is a way to test hypothesis using confidence interval. Okay, and of course, in the other case, if my confidence interval includes the value mu zero, then in this case, you can say that HO is supported by data. Okay, and then you do not reject HO. That's it. Okay. So it's easy, right? When you know the confidence interval, and then you test HO. Yeah, and remember that it only works for the two-tailed test. Okay. Remember that you can only do that for the two-tailed test. Okay. So it means that, okay, you have something like this, reject generation on the right and on the left. Sharing. Okay. Maybe we should take a break, right? Break not. Okay, let's take a short break for 5 minutes. You all can follow, right? Okay, take a short break for 5 minutes. Okay, we'll stop recording. Okay. Remind me to continue recording later. In 5 minutes, I take it back. Okay, any questions? Okay, so we continue. Okay, so using confidence interval, okay, we can test hypothesis. Okay, but it only works with the two-tailed test. Okay. Okay, so how about the other cases? You have two more approaches, okay, two more ways to test hypothesis. Okay, probably up to now, I think that the most common way to test hypothesis that you know is this one. Okay, using the test statistic, you draw the rejection region, and when the test statistic belongs to the rejection region, we reject. Okay, otherwise, we do not reject. Okay, with the level of significance alpha. Okay, so let's try with an example using this common approach. Okay, to remind you. Okay, you all hear me, huh? Okay. Testing hypothesis. Testing hypothesis. Okay, using the first approach. Okay. Using the first approach. Okay. So again, okay, now my statement, right, is to say that, okay, in my opinion, average age of all students in Vietnam is lower than 20.5. Okay. Okay, so why not? This is my opinion. So in my opinion, the average age of all students is less than 20.5. Okay, so again, you don't agree with me, right? So you like to yeah, prove that I'm wrong. Okay, so again, you first of all, you okay, write down H1 alternative hypothesis, not HO now, it become mu greater than equal to 20.5. Okay, so clearly you have the one tail test. But which one is it? Okay, have the one tail test. Now the rejection region, okay, is obtained when the test statistic is far above. It means on the right. So in this case, I have the right tail test. Okay, right tail test. Okay, and you want to test with significance level again, okay, for example, 5%, okay, which is 0.05. Okay, so the area of the rejection region is 0.05, which is 5%. Okay. Okay, and you don't agree with me again. Let me take a sample with n equal to 100. Okay, with 100 students. Okay, you ask. Okay, you try to collect data. You get X bar. Like before, I think I got something like 23, right? Until okay, or not. Okay, and I suppose the signal is equal to 2. Okay. Okay, and I like to test. You want to test agent. Okay, step by step. So the next step, so we follow the procedure. You write down H1. Okay, you write down the rule. The rule. Okay. You write down the rule. So what is the value of mu0 in this case? Mu0 in this case is 20.5. Yeah, so this is what we call mu0. Okay. This is the value of the parameter in the null hypothesis. Okay. Okay, so we know from CLT that okay, what do you know? Okay, S bar approximately follows the normal distribution with mu in sigma squared over n. Okay, but of course, in testing hypothesis, you don't know the value of mu. Okay, so we approximately take mu0 instead of mu. If its bar follows non-hypothesis, okay, with mu0 is square divided by n, approximately. Okay, then x bar minus mu0, okay, divided by sigma over root n, to follow standard normal distribution, right? Okay, and we use it for the test statistic. Okay, test statistic. Okay, helping you conclude or make a conclusion or decide if you reject Asia or not. Okay, so okay, we also need to draw this one. Okay, now this is the n01 standard normal, 0.5, so I need the critical value. 0.5, what is it? Is that 1.65? Okay. Okay, 1.64, thank you. 1.64, right? So now I draw. Wait a second. Need to. Okay. One second. Fine. I need some more battery. 1 second. Okay. I'm sharing. That's my. Yes. Okay. Test and statistic. Draw. Draw n01. Okay, rejection region. I know that now it is the right of test. And the one for the standard normal distribution. That 0.05, 1.64. Okay. Okay. So I calculate that statistic. If it belongs to the rejection region, I reject it all. Otherwise, I do not reject it all. Yeah, and I replace. I borrow 23.2 minus the value is 0 from, okay, now hypothesis 20.5. All right. Divide by sigma 2 over 10. Okay, how much do we get? How much do we get? Equal to 1.7 divided by 0.2 here. Okay, so 10.5. Okay, it's big, right? Okay. Thank you. So here I get something like a 2.7. Okay. 2.7 divided by 2. Okay, right. Okay, 13.5 for my PS. Okay, now I'm happy to get back to the curve diagram and see that my value of TS is somewhere here, okay, far above 1.64. That is my TS. Look at this. Okay, so clearly you can say that TS now belongs to the rejection region. Okay, I can reject HO at 5% significance level. Is that okay? Okay, I hope that everything is fine. Okay, so I think that is the most common way, right? Test hypothesis that you know up to now. Okay, however, there's another way, very convenient, especially when you use the software package using p-value. P-value. Okay, what is the p-value? Well, the third way to test hypothesis. The third way to test hypothesis is to use p-value. Okay, so what is the p-value? What is the p-value? P-value, by definition, you know p-value? Any of you remember what the p-value is? Okay, p-value, by definition, is the area of the rejection region when the test statistic is considered the critical value. Considered, okay, considered the critical value. Okay, so what does it mean? It means that in this previous example, I know the rejection region here on the right. Okay, but instead of writing down the area to be 0.05, no, I don't use it. Okay, I draw it and now I consider my TS to be this value. Okay, so TS, my TS before is equal to 13.5. Okay, now the idea of the p-value is equal to this area. Okay, very simple, right? Okay, you know the form of the test, right tail or the tail, left tail. Okay, you draw rejection region, you consider test statistics to be the critical value. Okay, so 13.5 and p-value is simply this area. Okay, so if I can go back here, what do you think about this value p? Actually, 13.5 is very, very, very far away. So the area is rather very small. Okay, so after getting p-value, so often it's not easy to get it by hand. Okay, it's possible with the standard normal distribution and z1. These are many tables value. But for t distribution for chi-square f, okay, it's almost impossible to get it by hand. We will rather refer to the software package in computer. Okay, but it's very convenient, right? So, okay, what can I say? So in this case, after getting p-value, we need to make a decision. Okay, if p-value is small, what do you think about the decision? Would you reject HO or not reject HO? Okay, make a guess. Okay, reject or not reject? Small. Okay, within with this one, in this case, you see that TS is very, very big, 13.5. Okay, so if I draw it, I get something like this, 13.5. Okay, if I draw it better, I get something like this. Okay. I think 13.5 is very, very, very far away. Okay, something like that. Okay, and the rejection region is here. So it's rather far away, far away. P-value is small. Okay, so I'm drawing. Okay, think about this again. For this case, right, because 13.5 is very far away like this. So do you think p-value here is small or big? Okay, p-value in this case, I mean this specific case. Do you think this one is big or small? If TS is 13.5 and 0.1. If you remember the standard normal distribution, Okay, I think the three standard deviation from the mean will already capture 99.8% the whole population. So it means that from here, okay, the area is very small already. Okay, so 13.5 is even, okay, is even further in the sense it's very, very far away from the value 0 here. So p value is very, very small. Okay, in my example, right? And remember that in my example, I reject HO. Okay, supporting the fact that, supporting the fact that, okay, the note for this example is supporting the fact that if p value is small, we rather reject HO. Okay, but how small? How small? Okay, if I test hypothesis at 5%, then I use alpha here. If p-value is small, in the sense that p-value is less than or equal to alpha, for example, 5%, 0.05, we reject HO. Okay, otherwise, we do not reject HO. Okay? Okay? So something that you have to know, right? And to learn in the sense that if p-value is more, then we simply reject HO. Okay, in practice, we get p-value from the computer software. Okay, and you make decision automatically. Okay. Okay, anything else about p-value? P-value can be seen also as the probability to get wrong when we reject HO. Okay. Okay. I think that's okay. There are several ways to define p-value, but this one it's easy to remember. This to me, p-value is probability to be wrong when we reject HO. Okay. So what does it mean? It means that if p-value is more than, okay, probability to be wrong when we reject HO is small. Okay, so we reject or not reject. Okay, if p-value is small, then the probability to be wrong when we reject HO, okay, then we reject. Okay, so rejecting HO. Okay, if p-value is big or large, okay, so in this case, probability to be wrong when we reject HO is big. Of course, we don't want, okay, the probability to be wrong to be big, right? In this case, better not to reject HO. Okay. Okay, once you know it, everything will become simple because you get the value automatically from the computer software. Okay, and you decide, make a decision right away. Okay. Okay, so you see that you don't really have to calculate by hand. The computer software will help you. Yeah, for most of the work. Also, you have to tell the computer what to do, what model, okay, what test to run and so on. But basically, we don't have to calculate by hand, which is a good point. Okay. So I hope that you got the ideas. Okay, but to summarize, have two ways to test hypothesis. Okay, for two-tailed test, you can use the confidence interval. Okay, okay, and the two other methods are the first one to use the test statistic, compare with the critical value. Okay, and the next or the last method is to use the p-value. Okay. Okay, of course, now, okay, p-value is still debated in the sense that in some areas like psychology, okay, medicine, p-value should be used with care. But in economics, for now, I think it's still okay. Okay, p-value is still widely used everywhere, and it's very convenient too. Yeah, save the file. Okay, so I think that we mostly thunderstorm light. Let me check again. Okay. So if you go back to the look at the slide, you see the summary. For the third approach using the p-value, we state the null hypothesis HO. Then we'll plan alternative hypothesis H1. You calculate the test statistic. You consider TS to be the critical value. Okay, you calculate the area of the rejection region, which is the p-value. Okay, often with the software help. And then you compare the p-value and significance level alpha. If p-value smaller than or equal to, even if it's equal to, we can reject H1. Otherwise, we do not reject H1. Okay. One like okay in here. Okay. P-value is also the smallest level of significance alpha at which H1 can be rejected. Okay. But to me, p-value is the probability to get wrong when we reject H1. And p-value is the area of the rejection region when Ts is equal to Pb. Okay. Okay, so I hope that you got the main ideas. Any questions? No. Okay, no questions? No. Okay, I have a few questions. Okay, so for the next slide, we will study next week. For now, I think that I can open a quiz. Okay, and for some questions you can answer together. Okay, what's the quiz? Okay. Okay, the other questions you answer at home. The first part will contain some questions to answer quickly. So I think that for this part you answer at home. Okay, and the next part is the MCQ. Okay. Okay, so for the some of them, I think that we can answer together. Okay, for example, confidence interval. Okay, this score associated is 99%. No. Okay. No, it's still the short questions to answer. No, this one. Okay. Oh, there are very quick. Okay. The answer. Some others take more time. Okay, so we can start reading the questions. Okay, very often the table values is very important. Yeah, so for now we mainly use the N01. Okay, standard normal distribution. Okay. Okay, question 1. Okay, if we construct 98% confidence level for the population mean, so what is the confidence level? Okay, that's a tricky question. What is the confidence level? Confidence level. Okay, careful because the confidence level is different from significance level. Okay, well, you remember when I say, right, confidence level? Yeah. I still don't see the right answer yet. Okay, this is a tricky question because, okay, I saw C, yeah, okay. Okay, you see why? Because, okay, confidence level is different from the significance level, right? Okay, when the test hypothesis significance level, alpha is small. but confidence level is often okay. So it's rather C. Okay, confidence level is rather big. Okay, don't get confused. Okay, thank you. I saw your answer. Okay, this one is tricky. Right, confidence level. Okay, actually it's automatically 98%. Okay, different from significance level. Okay, we use significance level when we test hypothesis. Okay, look not here. Okay. Oh, 98%. Okay. Next, this one I think you might need to use. Okay. So you from here 2.17. Okay, B is the right one. Okay. Okay. Actually, I record everything so I can check your answer later. Right? Okay, seems to me B is the good one. Okay, and you may wonder why. Right? Okay, so we already told me B. Okay. That again is refer to the answer one. Okay. The way to get it. 97. So I try to capture 97% of the home population. 97%, which is 0.97. Okay, so the remaining area is 3%. Okay, 3%. But divided by 2. Okay, so this area is 0.0015, something like this, right? Okay, and you get this score from the table. Of course, you need to use the table. That's 0.0015 if everything fine. Okay, 2.17. Okay. Question 3. Okay. Please follow your anything. Okay. So okay, you told me decrease. Okay, since to me decrease. Okay, the right one. Okay, let me check. Sample size increases, so it means n increases, right? Confidence interval for the population mean will. Okay, so they talk about the interval length, right? The length of the interval. Sample size increase. Okay. Okay, you can guess it. Okay, intuitively. Okay, either you refer to the formula, because you know that confidence interval is x bar plus minus z over 2. Okay, sigma over n, something like this, right? Sometimes you need to refer to this, and the length will be twice this quantity. Okay? Twice this quantity. The length. Length is the maximum minus the minimum. Okay? So the length will be twice that value. Okay, sample size increases. It means n increases. Okay, and increases. Okay, intuitively, when n increases means that we have more information. Okay, you have more information, so you should get a better confidence interval. So a better confidence interval will mean a smaller one or a bigger one. Okay, actually a smaller one. So intuitively, you may think that actually decreasing. Okay, decrease the answer. Okay, some of you are already sent me the right one. Okay, decreasing. You agree? Okay. Okay, you can also check, right? Intuitively, we may think that, okay, decreasing the right answer. Okay, using the formula, you can also check it, right? Because actually sample size increases, but we don't change the level of confidence. In this case, Z alpha over 2 doesn't change. Okay, sigma doesn't change, n increases. So sigma divided by root n decrease. Okay, supporting answer A. Okay. Okay, whichever way to answer should get the same point. The same answer, the conclusion in the end. Hypothesis testing now. 22. Okay, hypothesis testing. Okay, with that distribution. Okay. Okay, always try to understand the meaning, right? Meaning of the test. Okay, you know why? Because when you test hypothesis, especially for questions like this, okay, for econometrics and with the models, I think it's clearer about HO. But here, when they tell you the context, okay, it's like the story. Okay, so think about HO, H1. Okay, so you told me B, right? Okay, so let's check. It was reported that the population had a mean of 27. Okay, so we want to test this claim. They say clearly that okay, this one is HO and you want to test it. Okay, so HO here consists to say that mu is 27. Okay, so only we. Okay, we have a zero HO mu equals to 27. Okay, and clearly H1 is the negation of HO. Okay, you got it. Two here. Okay, two again. Okay, HO. I think it's the same question, but the only difference is the test statistic. Okay, they ask you what is the test statistic. Okay, HO, H1, we know them. So in order to test HO, we take a random sample of like 100. So you write down everything you know. N equal to 100, right? Okay, HO here. There's one there. Okay. Sample mean. So you take a sample and calculate the mean. You get X bar equal to 25. Okay, what is your answer already? Okay, B or D. Okay, let's see which one. Okay, okay, 25. Okay, and standard deviation. Okay. Okay, so it's like a sigma, right? Equal to 7. Okay, and test statistic equal to X bar minus mu divided by sigma over N. Okay. Okay. And you got, I think that it is the last one. Okay. Yeah, okay, thank you. Okay, and you need to keep this value. You need to keep these values for the next question. Let me continue. Okay, here. So it was the last time. Okay, answer. Okay, you can, oh no, this one's different.